All right, hello and welcome back. So this is another ALEKS topic that's called drawing the MO energy diagram. MO stands for molecular orbital energy diagram for a period 2 homodiatom. This is a requested video, so thank you, Nicole, for making this request. This is a pretty cool little topic, and I'm going to go through probably the whole learning progression here because there's a lot to unpack. So this video might be a little bit on the longer side, basically just because I want to make sure that we're talking through explaining what's going on, as we do this. And the first thing that I actually want to do is click on the explanation button here because there's a little slider tool that I think is really useful for us to sort of unpack what we're trying to do here, what we're trying to accomplish. So I'm going to go ahead and do that first. Then we will go back in and do some practice. But I actually wanted to start with these two energy level diagrams for homonuclear diatoms. Homonuclear means the atoms are going to be the same that make up our molecule. So the energies of their atomic orbitals would be the same, and then we're going to be overlapping those to create our molecular orbitals. So let's go ahead and unpack this one on the left-hand side first. So basically what this is showing us is that for our atomic orbitals, so if you just imagine like a carbon atom or a nitrogen atom or whatever, and we're just focused on this section here, that individual atom will have the following atomic orbitals. So that's what this AO stands for. The lowest energy atomic orbital will be the 1s, then the 2s, then the 2p. And I think that hopefully at this stage we're all pretty familiar with that, electron configurations, all that sort of stuff. So if you had a carbon atom, carbon has 6 electrons, then we would fill those in our atomic orbital diagram by putting in the electrons here, 1, 2, 1, 2, 1, 2, to fill in our atomic orbital electron configuration. So that's what this represents over here. Same thing over here. So because it's homonuclear, then that means that the atomic orbitals and really the energies of those atomic orbitals will be exactly the same. This represents, in this case would be one carbon atom, and this case would be another carbon atom as well. Now, for this topic, what we're really focused on is this bit in the middle. So this bit in the middle represents the molecular orbitals, and basically that's what happens when we mix these atomic orbitals from this carbon atom and these atomic orbitals from this carbon atom. We mix them together, they overlap with one another, and then we end up with this new set of orbitals. So these are basically, for all intents and purposes, very similar to the orbitals that we see here. In terms of filling in these orbitals, they're going to follow the same exact rules. Pauli exclusion principle, all that sort of stuff. That's going to be what we see here. And we're going to fill in from the bottom to the top. And basically, these are formed by this overlap between the atomic orbitals. So if you play with these sliders, you'll start to see that. So basically what we're indicating here, we've got a 1s orbital here, a 1s orbital here. Those are going to mix. Those are going to overlap. And as a result, we're going to get 2 new orbitals. This one is called the sigma, and it's labeled the 1s, so this represents sigma. We'll talk a little bit more about the difference between sigma and pi here as we get further into this video. But and the star, the asterisk, means it's an anti-bonding orbital. So if electrons are in this bottom orbital, that means that that's going to encourage bonding. That would be a bonding orbital. It's at a lower energy. And then the sigma star here represents an anti-bonding orbital. But anytime we're going to be overlapping 2 atomic orbitals, we're going to get out 2 molecular orbitals, and that's just sort of what we're seeing here. And we can sort of follow along here. For this is for group 5A and before. This is for group 6A and after. And what that really means, if we look at our periodic table, so up here we've got our labels 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So anything from 5A and before, so 1A to 5A, that's going to behave like this. That's going to be sort of what we see over here. Things that are from 6A and above, 6A, 7A, 8A, theoretically, those are going to behave like this. And you'll notice from the beginning, they're the same until we get up here. So I'll get to there in a second. So here we're showing the overlap between 2s, 2s, sigma star here, and our bonding orbital here, just a sigma 2s. Here is where we're going to start to see a difference. So for group 5A and before, the bonding pi molecular orbital is actually a lower energy than the sigma orbital here. And again, I'll talk a little bit more and sort of show what this really means and what this looks like. And for group 6A, the lowest energy orbital, that's a molecular orbital that's formed from the p overlap of the p orbitals, is going to be a sigma orbital, sigma bonding orbital here. So that's a difference that we need to pay attention to. It's definitely going to come up in this problem, I'm sure. And then, you know, otherwise everything else is the same essentially. So this is the difference, the thing that we're going to be looking for group 6A and after. The ordering of our molecular orbitals is going to go sigma, pi, pi star, sigma star, whereas the ordering for overlap of our p orbitals in group 5A and before is going to go pi, sigma, sigma, or pi star, sigma star. So that's something we need to pay attention to. Okay, now I want to talk a little bit about what these, you know, the difference between a sigma and a pi are. And I'm going to start with our s orbitals. So I'll move this over here a little bit, and we'll move this back to here. Okay, so if we have two atomic orbitals, so this would represent here, you know, this side here is this blue dot, this side here is this red dot. Those two are going to combine. We're going to combine those atomic orbitals. They're going to overlap. We're going to end up with these molecular orbitals. So this is sort of just giving you a visual of what's going on in this sort of, you know, part of the diagram. So we're going to have a bonding orbital, which is a sigma bonding orbital here, and we're going to have an anti-bonding sigma star orbital, which would be represented by this here. This would be relevant or sort of valid for the 2s energy level as well. So, you know, this sort of thing here is exactly what's going on. We're going to overlap. We're going to form a bonding orbital where their electron density will be between the two. These represents the nucleus of the atoms. So if the electron density is between them, that represents it's going to hold these two things together. That will be bonding. If the electron density, so these, you know, shaded parts, that represents where the electron density would be, that's going to be an anti-bonding because the electron density is essentially pulling them away as opposed to holding them together. So this is sort of what's going on for the 1s case and the 2s. Now the p orbitals, of course, p orbitals are more, you know, challenging. There's more going on. So for the p orbitals, this is what would be represented by the sigma. So this represents the sigma, and really the difference between a sigma bond and a pi bond is the way in which they are formed and the where the electron density is. So if the electron density is directly in between the two nuclei, that represents a sigma bond, whereas a pi bond looks like this, right? So this, if you're familiar with double bonding, triple bonding, and you're familiar with pi bonds, same concept, where we've got our overlap here between these two p orbitals. These are our atomic nuclei, and then we've got the electron density sort of above and below this plane here. That represents a pi bond. This would represent a pi star anti-bonding, bond essentially. So the difference between the labels of, you know, sigma versus pi, that just means where the electron density is. Here it's in between the nuclei. Here it is sort of above and below that plane where the nuclei, live essentially. So that's sort of a visual. Hopefully that helps a little bit. But let's go ahead and jump into this. Actually, do the problem. So to do the problem, I sort of put together this little, I love these little sort of step-by-step processes. Number one, count the number of electrons in your molecular ion or molecule. That is always going to be the most important thing. You can use the periodic table here to help you if you just want to make sure. So here we've got lithium. Keep in mind that we've got lithium 2, and then we've got 2+. So the way I would sort of count this, one lithium atom will have 3 electrons. So I would have 6 since I've got 2. Since it's 2+, I've only got 4 electrons that I need to deal with. So step 1, determine the number of electrons that we have. So in this case, 4. Determine if the diatomic is in group 1A to 5A or 6A to 8A. In this case, it's actually not going to matter because we've only got 4 electrons to deal with. But it is a good practice just to sort of keep that in mind. Lithium is in group 1, so we would be sort of using that, that first, option essentially in terms of the ordering of those p orbitals, p molecular orbitals. In this case, like I said, because we've only got 4 electrons, we don't need to worry about that. But I'm sure in other examples we will need to worry about that. Then we're going to draw the appropriate molecular orbital diagram, and then finally fill in the electrons from the bottom up. Now, in terms of drawing this, if you don't, don't remember how to do this, I do think that having a cheat sheet, sort of having that, that next to you is fine. However, if our goal is to really learn and retain and be able to do this, on an exam or something like that, it definitely is good practice to just be able to draw this whole thing out for, that group 5A and below and group 6A and above. And the way that you're going to get that is just by practicing it, right? If you're always looking at your notes, your brain won't think that it's important for you to actually learn and retain that. It will just say, well, let's look for that sheet. So here, I think it is a good place to practice, filling this in, writing this out. But this is the answer for the first one. Again, this part of the diagram, let me switch this. This part of, I just want to have a pointer. This part of the diagram, right, of sigma 1s, sigma 1s star, that's going to be the same essentially, right, for the 1s, the 2s situation. If we got up to the p orbitals, then we'd have to, take into account, is it group 1a through 5a or 6a and above, and deal with that. But let's go ahead and check this one. Yay, we'll move on to the next one. Again, following our ordering, we want to figure out number one, what's the number of electrons? So O2, oxygen has 8 electrons total. And here it is good to point out, we're talking about total electrons. We're not just talking about valence electrons here. So total electrons, 8 times 2 is 16, plus 1, because we got O minus, would be 17 electrons. That's what we need to keep in mind. Determine if it's in group 1A to 5A or 6A. Oxygen's in group 6A, so we're going to have to use that sort of, that second option here for building our structure. Draw the appropriate molecular orbital diagram. So let's go and do that. So this is a little bit tedious, I will admit. Here we've got to plug these in. The 1s. Now we've got sigma 2s, or sorry, 1s star. Then we've got sigma 2s, sigma 2s, sigma 2s star. Now we've got our sigma 2p, right? And here's where, really we've got to be careful, right? We've got to really make sure that we're doing this properly. Then we've got our pi 2p, and we've got 2 of those, right? So again, I know that we've got 2 of them just because I know that I have experience. I remember what these are supposed to be. So if you don't, if at first you're struggling with that, just take your time. You'll get there. And then 2p. Oops, I keep forgetting to subscript it. 2p, as you guys can see, and 2p star. So once you've done all this, it definitely is a good idea to just go back over, make sure that you've constructed this properly. We've got we should go bonding, anti-bonding, bonding, anti-bonding, and then make sure that, because this is group 6A and above, we want to make sure that we've got this right ordering. The sigma is going to be lower energy than the pi bonds. For the pi bonds, we should have 2 orbitals for those, and, bonding here, anti-bonding here, everything looks good. Now we'll go ahead and fill in the electrons. I think it makes most sense just to sort of fill in these, up arrows first, then start filling in the bottom arrows. And then let's count. So we've got 2, 4, 6, 8, 10, 12 so far. Oops, I'm gonna definitely want to make this look better. So this would be 14. This would be 16, and that would be 17. Okay, so however you fill it in, right? You just got to get those electrons in there. But just again, reiterating, we have 8 atomic electrons times 2 is 16, plus 1 is 17. 2, 4, 6, 8, 10, 12, 14, 16, 17. We should be good. Okay, so this video is going to cut off at 30 minutes. So, or sorry, 30 minutes, 15 minutes. So I'm not going to do this next one because I don't want to just start it and then get cut off. But, basically, again, just go through your process here, count the number of electrons. So neon 2 with a 2+ charge. So that's going to be, 20 electrons minus 2 electrons, 18 electrons. It is in group 6A to 8A. So, make sure you've got that right structure. just like the one we just drew, draw it out, and then fill in the electrons. So hopefully that helps, Nicole. Definitely let us know if there's any questions in the comments below.